right, so Chapter 7 is on sampling distributions, and this is really a foundational, underlying chapter for the rest of the year. So we'll learn a lot of foundational concepts in this chapter that we'll use later. In 7.1, we're going to talk about sampling distributions. Now, 7.1 is actually day 1 and day 2, but day 1's really short. So I'm going to try to fit day 1 and day 2 into this same PowerPoint. Okay, you can read through that list, pause it and read through that if you want. That's everything we're going to do here. Okay, so the process of statistical inference involves using information from a sample to draw conclusions about a wider population. That's why we have sampling in the first place. And statistical inference is that process of making decisions, drawing conclusions. Different random samples yield different statistics. We need to be able to describe the sampling distribution of possible statistic values in order to perform statistical inference. This concept of sampling distribution, again, is a concept that we'll use throughout the rest of the year. We can think of a statistic as a random variable because it takes numerical values that describe the outcomes of the random sampling process. Therefore, we can examine its probability distribution using what we've learned in Chapter 6. So here's the process of sampling. We take a sample, a representative sample, then we use that sample to make some kind of conclusion about the population. That's inference. Okay, parameters and statistics. We've already talked about this before. As we begin to use sample data to draw conclusions about a wider population, we have to be clear about whether a number describes a sample or a population. So a parameter is a number that describes some characteristic of the population. In statistical practice, the value of a parameter is usually not known because we cannot examine the entire population, usually. So a parameter would be like mu or sigma. A statistic is a number that describes some characteristic of a sample. The value of a statistic can be computed directly from the sample data. We often use a statistic to estimate an unknown parameter. So an example of a statistic would be like x bar and s. X bar being the statistic that's trying to approximate mu, and s being the statistic that's trying to approximate sigma. Population mean, population standard deviation. So S and P, statistics come from samples, parameters come from populations. Oh, here we go. Mu, the Greek letter mu for the population mean, and X bar for the sample mean. P, so this one's not one that I just referenced, P represents a population proportion, and the sample proportion P hat is used to estimate the unknown parameter P. So identify the population, the parameter, the sample, and the statistic in each of the following settings. So A, there are a couple problems in the notes like this. There's also a couple problems from your homework that are just like this. The Gallup poll asked a random sample of 515 U.S. adults whether or not they believe in ghosts. Of the respondents, 160 said yes. So I'd encourage you to actually read through both A and B. If you want to, you can pause the presentation at this point and see if you can do A and B without me. But I'm going to go ahead and go through them now. So the population in this one is all U.S. adults. The parameter is the true proportion of U.S. adults that believe in ghosts. The sample is the 515 U.S. adults. And the statistic is the 160 out of 515 U.S. adults that said yes. So that, in this case, the proportion is 0.31. 160 out of 515 gives us a p hat of 0.31. Basically 31% of my sample said they did believe in ghosts. Okay, B. During the winter months, the temperatures outside the Starnes cabin can stay well below freezing for weeks at a time. To prevent pipes from freezing, Mr. Starnes sets the temperature at 50 degrees Fahrenheit. She wants to know, Mrs. Starnes, she wants to know how low the temperature actually gets in the cabin. A digital thermometer records the indoor temperature at 20 randomly chosen times during the given day. The minimum reading is 38 degrees Fahrenheit. Okay, so in this one, the population is a little different. It's all the different temperatures in the cabin throughout the day. it would probably be represented most easily with a graph of some sort. Basically, if we were to graph all the temperatures throughout the day in the cabin, that would be the population. The parameter is the true minimum temperature, the lowest that the temperature gets in the cabin throughout the day. The sample is the 20 randomly chosen times during the day. The statistic is 38 degrees. Basically, that one minimum reading that we got from our sample, that's the statistic that we're interested in on this one. So that's a little different because it's not like we're not talking about X bar, we're not talking about S, we're not talking about P hat. It's just the minimum reading is the statistic. Okay, this basic fact, there's, I think we missed something here. Sampling variability, there's part of the slide that's missing. So, there we go. How can X bar be an accurate estimate of mu? After all, different random samples would produce different values of X bar. Okay, so it kind of makes sense that every time you take a sample, so here's my population, and here's, in this picture, it's representing like 8 different samples. And every time I take a different sample, I'm going to get a different estimate. But if the sample's done correctly, it's going to be an approximation of the true parameter. The fact that you get this variability, every time I take a sample, I'm going to get a different estimate. This is called sampling variability. Sampling variability is not really a bad thing. It's expected when we sample. When we sample, it's expected that I would get a slightly different answer, a slightly different estimate every single time. That's just the nature of sampling. So, to make sense of sampling variability, we ask what would happen if we took many samples. So that's really what we're going to talk about the rest of this lesson, is what happens when we sample, if we were to sample over and over and over again. This gives an example. We're not going to do this activity reaching for chips, but we are going to do a similar activity in class. This shows, just to kind of walk through the concept in case you miss class, if we take a sample of 20 chips and then record the sample proportion of red chips, and then return all the chips to the bag, and if we graph all of those sample proportions of red chips, we would get a graph that maybe looks something like this. And again, we're going to do this activity in class, but this is an approximation of something called a sampling distribution. And we're going to look at that in a minute. So in the previous activity, we took a handful of different samples of 20 chips. There are many, many possible simple random samples of size 20 from a population of size 200. If we took every one of those possible samples, calculated the sample proportion for each, and graphed all of those values, we'd have a sampling distribution. Now, the concept of sampling distribution is a little overwhelming because usually there's so many outcomes that it's almost impossible to graph them all. So in this case, how many different possibilities are there for 1 out of 20 reds? How many possibilities are there for 2 out of 20 reds? How many possibilities are there for 3 out of 20 reds? And I graph them all. And there's a lot in this sampling distribution. It's a little bit unrealistic to graph them all. So usually we use some kind of simulation or even sampling to approximate a sampling distribution. The sampling distribution of a statistic is the distribution of values taken by the statistic in all possible samples of the same size from the same population. In practice, it's difficult to take all possible samples of size n to obtain the actual sampling distribution of a statistic. Instead, we can use simulation to imitate the process of taking many, many samples. One of the uses of probability theory in statistics is to obtain sampling distributions without simulation. We'll get to the theory later, so that's something that we'll do later. There are actually 3 distinct distributions involved when we sample repeatedly, which usually we don't sample repeatedly, but we're talking about theory here, involved when we sample repeatedly and measure a variable of interest. So 1, the population distribution gives the values of the variable for all the individuals in the population. And then the distribution of sample data shows the values of a variable for all the individuals in a sample. This one is really the smallest one. Basically, take a sample, look at what you've got. That's the distribution of a sample. But the sampling distribution is really probably the most overwhelming one. It shows the statistic values from all of the possible samples of the same size from the population. And there is a difference between all these three. Population distribution is, okay, what's the actual population look like? The distribution of a sample is, okay, what did my sample actually look like? And then the sampling distribution is all possible samples from the population. Here's kind of a picture that shows them. In this case, if I was talking about red and blue chips in a bag, my population distribution is just 50%, 100 red, 100 blue, so basically 0.5 for each. My parameter is P equals 0.5. Now, usually we don't know what the population distribution is. This is usually not known to us. Then when we take a sample, this is 3 different distributions of samples. So distribution of sample, here's one sample. That's the distribution of one of the samples. This is a distribution of another sample. This is a distribution of another sample. So this is actually 3 different sample distributions. On each of them, I got a different p hat. That's normal. But then the sampling distribution is if I graph them all. So if I sample over and over and over and over and over and over and over again, and I graph all of those p hats, that's the sampling distribution. The fact that statistics from random samples have definite sampling distributions allows us to answer the question, how trustworthy is a statistic as an estimator of the parameter? To get a complete answer, we consider the center, spread, and shape. In the chips example, we collected many samples of size 20 and calculated the sample proportion of red chips. How well does the sample proportion estimate the true proportion of red chips of 0.5? Now, this is the sampling distribution of that red and blue chips. Notice that the center of that sampling distribution is 0.5. In fact, if we took all possible samples of size 20 and found the mean of those sample proportions, we'd get exactly 0.5. This is an example of an unbiased estimator. In an unbiased estimator, you will always get the center of the sampling distribution will always be the population parameter. Okay, so a statistic used to estimate a parameter is an unbiased estimator if the mean of its sampling distribution is equal to the true value of the parameter being estimated. X bar is also an example of an unbiased estimator. It will always be an unbiased estimator of mu. P hat is an unbiased estimator of P. Okay, I'm going to kind of whip through a few things just because we're running out of time for my 15 minutes. To get a trustworthy estimate of an unknown population parameter, start by using a statistic that's an unbiased estimator. This ensures that you won't tend to overestimate or underestimate. Unfortunately, using an unbiased estimator doesn't guarantee that the value of your statistic will be close to the actual parameter value. One way to conquer this is to use a large sample. Larger samples have a clear advantage over smaller samples. They are much more likely to produce an estimate close to the true value of a parameter. So if you use a larger sample, you have less variability, and therefore you'll be more likely to be closer to your population parameter. If you use a smaller sample, 100 is still a pretty good sample, but you're more likely to get a sample proportion that's farther away from the true value of your statistic with a small sample. The variability of a statistic is described by the spread of its sampling distribution. This spread is determined primarily by the size of the random sample. Larger samples give smaller spread. The spread of the sampling distribution does not depend on the size of the population as long as the population is at least 10 times larger than the sample. Okay, quick discussion. This is our last thing. Bias means that our aim is off and we consistently miss the bullseye in the same direction. Our sample values do not center on the population value. High variability means that repeated shots are widely scattered on the target. Repeated samples do not give very similar results. So here's an example of high bias, low variability, low bias, high variability, high bias, high variability, and the ideal no bias, low variability. So if possible, choose a way that gets you low bias and minimum variability, accuracy and precision.